In this video, we are going to do one example of the solutions, series solutions about a singular point using the method of Frobenius. So I'm going to do problem number 15 from the textbook, and you'll see why I'm only going to do one problem once we do it. So we're going to start off with 2x, y double prime minus y prime plus 2y is equal to 0. And it tells us in the instructions to find a solution centered around x equals 0, but the x equals 0 is a singular point. So we need to use the method of Frobenius, which is going to be to use y equals n equals 0 to infinity, Cn, and we're going to do x to the n plus r right now, which is the same thing. I'm just going to say this for later that the x's can come through because they don't, anything that doesn't contain an n can come through. So it's the same thing as this. That'll be important for you to realize later because we're going to have this kind of solution that we are going to recognize from last section, and we're going to multiply it by this x to the r in the end to get our series solution for that piece. So we're going to go ahead and take our derivatives, but unlike last time, we're not just going to be able to right away easily manipulate the indices and exponents and things like that. We're going to have to get to the point where we can do some work on this. And we need a second derivative. All right, so let's go ahead and look at what 2 times the second derivative is going to be here. So that's going to be n equals 0 to infinity, n plus r, 2 there, n plus r minus 1, and a x makes this x to the n plus r minus 1. And then we have minus prime is n equals 0 to infinity, n plus r, Cn x to the n plus r minus 1. And then we have this over a little bit, plus n equals 0 to infinity, 2, and then that is Cn x to the n plus r, and that equals 0. And I'm just going to go ahead right now and pull out the x to the r that's common in everything here, and leave that sitting out there, equals 0. So this is n equals 0 to infinity, 2, times n plus r times n plus r minus 1, x to the n minus 1, minus n equals 0 to infinity, n plus r. I missed my constant here. This is Cn x to the n plus r minus 1. This is Cn x to the n minus 1. minus n equals 0 to infinity n plus r Cn x to the n minus 1 plus 0 to infinity whatever. Okay. We'll just leave it. It's going to be difficult tonight. There we go. 2 Cn x to the n. Now, we have these two can combine. N equals 0 to infinity. Yeah, I'm just gonna quit messing with that. So n plus 2 times n plus r times n plus r minus 1 minus n plus r Cn x n minus 1 plus n equals 0 to infinity to Cn xn, and then that equals 0. So we're going to have ignore the XR part for right now. That'll come back later in the problem. We need n equals 0 to infinity of 2 times n. Let's actually combine these. Let's make n plus r times 2n plus 2r minus 2 minus 1 Cn x to the n minus 1. So that is putting that 2 in there with this factor and then subtracting the 1 because the n plus r is a common factor that I factored out, plus n equals 0 to infinity, 2 Cn xn equals 0. So this is starting at 0. This is starting at -1. So -1 is lower, so I'm going to bring this series up by taking a term out. So that is going to be when n is 0, we have r times 2r minus 3 x to the -1st plus n equals 1 to infinity n plus r 2n plus 2r minus 3 Cn x to the n minus 1, and that is plus n equals 0 to infinity 2 Cn xn, and that is equal to 0. You can see right now here why x equals 0 is a singular point because I have an x to the -1st in the problem here. So this is x to the -1st is not ever going to be equal to 0, but I don't want that part to be equal to 0 anyways. I'm going to want r times 2r minus 3 to be equal to 0, meaning r is equal to 0, or r is equal to 3/2. Hang on to those. We're going to use those in a little bit to give us the r values here, and we're going to have two cases that are going to give us two different equations. Those r's are going to play a role in this. Let's go ahead and break this piece down though, where we're going to make this n equals 0 to infinity, n plus 1 plus r times, and then 2n plus 2 plus 2r minus 3, cn plus 1, x to the n, plus n equals 0 to infinity, 2cn x to the n equals 0. Give myself a little bit of space here. And combining those, n equals 0 to infinity of n plus 1 plus r times 2n plus 2r minus 1, cn plus 1, and then plus 2cn, all of that x to the n equals 0. Okay, so now I'm going to take just this coefficient part equal to 0. I don't want the x to the n to be 0. That doesn't help us. So n plus 1 plus r times 2n plus 2r minus 1, cn plus 1 plus 2cn is equal to 0. And I'm going to have two cases. So the first case is when r is equal to 0. So case 1 is r equals 0. Case 2 is r equals 3/2. And this then turns into, if r equals 0, this is n plus 1 times 2n minus 1, cn plus 1 plus 2cn equals 0. If r is equal to 3/2, I have n plus 1 plus 3/2 is 5/2. 2n plus 3 minus 1 is 2n plus 2, cn plus 1 plus 2cn is equal to 0. So here I have n plus 1, 2n minus 1, cn plus 1 equals negative 2cn, and cn plus 1 is equal to negative 2cn over n plus 1 times 2n minus 1. I'm going to finish up case 1 before I look at case 2. So C0 is equal to C0. C1 is going to be 2C0. C2 is going to be 4/9 C0. Let me go ahead and work that one out for you. This one was pretty straightforward, that 2 goes into 2 there, and sorry, with this is n equals 0. When n equals 0, this is negative 2C0 over 1 times negative 1. So that makes it 2C0 when n equals 1. Here, this is negative 2C1 over 2 times 1. So that's negative 2 C0, or negative 2 that's negative C1 which is -2c0. There we go. And then come on down a little bit more, actually a lot more. C3 is when n equals 2. Is going to be -2c2 over, then that's going to be 3 times 3. So that's going to be -2/9 c2, which is -2/9 times -2c0, which is 4/9 c0. And that's enough for me to write that y1 is equal to, and I'm just going to use a big C1 here, times x to the 0, x to the r, comes back into play here. Remember that that got factored out in front of the part that looked like our normal solution. So now for all of this that comes from this power series that we see here. So this is one of these constants, and then 2x, and then minus 2x squared, and then plus 4/9 x cubed. Then the next one will be minus, and that's part of my answer. The next part of my answer here, I'm going to factor out this 2 and put it in there to make this 2n plus 5, n plus 1, cn plus 1, plus 2cn equals 0. 2n plus 5 times n plus 1, cn plus 1 equals -2cn, and cn plus 1 equals -2cn over 2n plus 5 times n plus 1. And C0 is going to be C0 again. When n equals 0, C1 is equal to -2C0 over 5. And when n equals 1, C2 is equal to -2C1 over 9 times 2 is 18. So that's -C1 over 9. And that is make sure I got that right. No, this is not 18. This is when n equals 1, it's -2C1 over 2 plus 5 is 7 times 2. Those 2's cancel, that's -1/7 C1, which is -2C0 over 5. So that is 2 over 35 C0. When n equals 2, we have -2C2 over, there's my 9 and my 3. So that is -2 over 27. C2 is 2 over 35 C0. And so that makes a -4 over, and then you can do this in your calculator, that's 945 is what I got. And that makes my other piece of my answer here. Y2 equals big C2 x to the r there was 3/2, and we have 1 minus 2/5 x plus 2 over 35 x squared minus 2 over minus 4 over 945x cubed, and then that's going to be plus something. So my total solution, y, is going to be C1 times all of this. Make that kind of a big C1. Plus big C2, x to the 3/2 times all of this. And that's it. Just that one problem you can see took over 20 minutes for me to do. So that's why I'm only going to do one of these problems for this section, though I recommend that you give several more a try. Just give yourself plenty of time. So if you're looking in the textbook for some problems to do, this was number 15. You can also try number 17, 19, 21, and 23 are all like this. They do get more difficult as you go along, but the process is to go ahead and put that extra plus r in the exponent, include that in your derivatives, and you're going to get several r values that are going to split it up into several cases, sometimes only 2 cases, sometimes 3 cases or more, and you'll get a y equals equation for each of those cases that you find an r value for. So the more r's you get, the more answers you get. The textbook tells you what happens if you get a repeated r value. You know, you get an r to some power, and how you handle that. I'm just doing the most basic of the cases here to give you an idea. Read more on the textbook. This is usually not something that we do a whole lot with because we know pretty quickly whether 0 is an ordinary point or a singular point. If 0 doesn't work, then we center our series somewhere else, just like with the series that you learned in Calculus 2 for ln of x. And you said, well, I can't stick in x equals 0. I can't center it there because there's a vertical asymptote there. So you wrote the series centered at x equals 1 instead. So yes, you could go through this process and you could figure out what a series would look like centered at 0. But just don't do it if 0 is not in the domain. And find something that is in the domain that's not a singular point and write your series there. So this method, it's great for what we call pure mathematics, to just know that you can do it. Very rarely would you want to do this in applied mathematics, but it's part of the core objectives of the class. There it is. We've done an example. Maybe I can come back to some more examples of this in the future, but it's just way more time right now than you or I have time for in these videos, because we have other topics to get to that are really important. So when I come back next time, I'm going to pick up on the content in chapter 7, where we start to talk about Laplace transforms. And that's a really important thing for you to learn about those transforms. And so we'll get back to that next time when we start to talk about 7.1. See you for the next video.